1.2. Comparing rates of change in linear and quadratic functions. What is the difference between f at x equals 3x plus 1 and g at x is equal to 4x squared plus 3x minus 1? What's the difference between these? Well, first of all, and some of you are going, well, one's called f, the other's called g. I think we need to dig a little deeper. For example, the first one actually represents a linear function, so the graph of it is actually a line. The second one, the graph represents a quadratic function. Now, what's more important than that is that they have different degrees, and we're not talking about a bachelor's or master's or PhD, but we're talking about the highest exponent of each of these two equations. The degree is basically, when you look at the terms in the equation, when there's a single variable, we look at the highest exponent. The exponent on this is a 1, folks. And the exponent on this one, this is the highest one, is a 2. So the first one has a degree of 1. Every linear function, every line, has a degree of 1. The quadratic has a degree of 2. Remember again, a degree is basically the degree of a polynomial with a single variable, say x, is the value of the highest exponent. So the highest exponent here for x is 1. The highest exponent in this one is 2. So 2 is the degree for every single quadratic. 1 is the degree for every linear function. Moving on. Remember when, in grade 9 and 10, you looked at something called first and second differences? What did it mean when we looked at first and second differences? Remember that in linear functions, as long as the x's followed a pattern and the first differences followed a pattern, it turned out to be a linear relationship. So the degree of 1, which is a linear function, also has the first differences that are the same. Interesting. 1 degree, first differences are the same. Now, what else we learned is that in quadratic functions, provided that delta x was the same and delta y, the second differences were the same, then it represented a quadratic relationship. Now wait a minute, we didn't talk about deltas. Well, let's look at some examples and see what this refers to. Before we do that, let's remember that degree 2 is a quadratic and second differences are the same. So example 1, determine whether the following functions are linear or quadratic. So before we talk about deltas, let's look at equations. You need to be able to identify from the equations whether it's linear or quadratic. So the first example, note we have brackets. Something's wrong here. And that's right. When we have brackets, the first thing we need to do is expand. You have to expand it in order to find out the degree. Degrees can only happen when the equation is in expanded form. So now we're going to multiply negative 2x times x, so negative 2x times x, and negative 2x times negative 1. The result will be negative f at x equals negative 2x squared plus 2x. Now, looking at this, what's the degree of this function? Well, we look at the x. This has an exponent 1. This has an exponent 2. 2 is the highest, therefore this has a degree of 2. So because it has a degree of 2, what kind of function is this? That's right, it's a quadratic. Let's look at the next one. Now I want to expand this. 5 times x, 5 times minus 5. We expand it. Remember that you cannot determine a degree until you've expanded the equation. Expand the equation, find the highest exponent. Degree is 1. X has an exponent of 1. Degree of 1 means, therefore, this function is linear. So, you can look at the equation to determine if it's quadratic or linear, but better yet, you need to prove it. By proving, you use the degree to prove whether it's linear or quadratic. Now, let's look at examples with tables of values. All right. So, when you determine the type relationship, you have three options. One of them is unable to determine. You're unable to determine when the x's do not follow a pattern. 2, you can determine if it's linear if you have delta x and delta y are the same. So I'm going to go through this. I'm going to list this for you. We're going to go back a step and list all of these for you. Just a minute. Okay, remember earlier I talked about something involving deltas. Well, let's look at relationships from a table of values. Before I look at examples, I want to go over how to determine the type of relationship from any table of values. Now remember, you must put the table of values in order. So if you have a table with x's and y's, for example, let's just do x's and y's, you always have to put the x in order from lowest to highest. The y values follow with the x's. So this is going to be important. So again, you put the x's in order and the y values follow the x's when we put the x's in order. Once you do that, you then look at the x values. So how does that help us? Well, first of all, delta x, when you look at the delta x, how does the x's change? Delta means change. So this symbol is delta. It's a triangle symbol, a Greek letter, and it represents change. How do the x's change? If the x's change in a weird pattern, so that they're all different values as they change, then you must make the following statement: unable to determine. You're unable to determine the type of function from the table because the delta x's are different. Next, if you have delta x is the same and delta y is the same, this means that the function is linear. That's right, linear. It's linear because the x's follow a pattern, so the delta x values are the same, and the y's follow a pattern. That means delta y has the same number. Because of that, you can say that because the first differences are the same, the function must be linear. Now, what happens if you have delta x the same, but delta y is different? Well, you go on to do delta delta y. Sometimes delta delta y is the same, and that means the second differences are the same. And the second differences means that it must be the quadratic relationship, because again, delta y is the first difference, delta delta y is the second difference. So second difference means quadratic. Now, on the rare occasion that you're given an example where delta x is the same and delta delta y is different. So you've done delta y, that's different, and delta delta y is even different. Well, at this point in time in this course, folks, we have to say the following: neither linear nor quadratic. Why do we say that? Because oftentimes there's actually another relationship with those values and we haven't yet determined it. So we'll come back to this later on in this course when we have to deal with different tables. But at this point in time, you'll be asked to identify whether it's linear, quadratic, or neither. Sometimes you may have to write unable to determine. That's because the x's actually don't follow a pattern. All right, let's look at examples. So, you're asked to determine the type of relationship, and here we go. Here are our two, here's one table, and here's the other table. Okay, here are the two tables that I'd like you to determine the type of relationship. Now, looking at these two tables, let's see what we need to do. Very first thing you have to ask yourself is, are these numbers in order? No, they're not. The x's must be in order before you can do anything else. So we need to put them in order. Now, the lowest x here is -5. With -5 becomes the number 17. So negative 5, 17. The next number is negative 1. Negative 1 follows with 7. Negative 1 and 7. Next, 3 goes with 1. 3, 1. Next, 7 goes with negative 1. 7 and negative 1. Now we have placed this table in order. Here it is. Once we've done that, we now have to look at the next part, and that is, what is happening with the x's? Is there a pattern with these numbers? That means we have to do something called delta x. What does delta x mean? Is asking, what is the change in these numbers? What's happening to these numbers? That is, from negative 5 to negative 1. How does negative 5 become negative 1? Well, we have to add 4. That's right, you're adding 4. And from negative 1 to negative 3, we add 4. Now, let's look at all of this. This is a lot of information popping at you, so we'll do it slowly. So we're looking at add 4. Again, add 4. Again, add 4. What do you see here? That's right. You should see that all those numbers are the same. So, because these numbers are all the same, it means it gives us permission to go on to delta y. We do not have permission if these were different. So that's why you have to put them in order. You put them in order, it gives us permission, because they're all the same, to now do delta y. So, what is the next part, delta y? How does 17 become 7? Well, minus 10. How does 7 become 1? Minus 6. How does 1 become negative 1? That is minus 2. Notice that these numbers are different. Because they're different, we have to keep going. First differences are not the same. So now we go and do the second differences, which is delta y. Delta y says, how do these numbers change? From negative 10 to negative 6, it goes up 4. And negative 6 to negative 2, it goes up 4. What does that? Oh, look! Look at these numbers. You see that these numbers are the same. Because they're the same, that tells us that our delta x's are the same and the delta y's are the same. That is, the second differences means that, lo and behold, we have a quadratic relationship. That's because delta x and delta y are the same. Okay, try the next one. Let's stop the video now and try the second table, and then restart the video after you've put them in order first. Alright, welcome back. We've put these in order, and you should have gotten these values here. Remember that the y's follow the x's. It has nothing to do, the y values depend on the x. The x is what has to be in order. What's the first step that you have to do? That's right, we have to put the x's in order, delta x. So negative 11 to negative 6 is positive 5. Negative 6 to negative 1 is positive 5. Negative 1 to 4 is positive 5. 4 to 9 is positive 5. So we found out that the delta x values are all the same. What does that mean? It gives us permission to now do delta y. We now do delta y. 17 to 7 is minus 10. 7 to negative 3 is minus 10. Negative 3 to negative 13 is minus 10. Negative 13 to negative 23 is minus 10. That's right. All of these delta y's is minus 10. So the delta y values are the same. So we have the delta x is the same and delta y is the same. We can make a statement. Yes, that's right. This represents a linear relationship because the delta x and the delta y have the same values. Delta x is the same and delta y is the same. We don't have to worry about these numbers being the same. It's the column that has to be the same. Okay, next. Moving on to the next example. A function has the following domain and range. The domain is t is between 1 and 3, and the range is g at t is between -4 and -1. You're asked to sketch a linear function with these characteristics and a quadratic function with these characteristics. So you have to understand how to draw this. Well, first of all, you have to understand how to read this. It's saying the lowest domain is 1. The highest domain is 3. So it goes from 1 to 3. And the range goes as low as -4 all the way up to -1. So when we draw our graph, so we're going to move to the next page and create a graph. Okay, so we need a graph. So here's our graph and here's our domain and range copied again. So we need to find -1 to -3 in the domain. Okay, there's, sorry, -1 to +3, that's right, and -4 to -1. So there are positive and negative x values and only negative y values. So we want to draw the axis so that it covers all of this, but not with too much space. So our t is our x-axis, our y-axis is our g at t, and now we're going to graph this. Ready? So -1 is our lowest domain, and our lowest range is -4. So it's like plotting. We're trying to do an example. It doesn't mean that it has to be this example. We're trying to draw an example that represents this. So I'm taking the lowest and the lowest and writing it here. That is my lowest domain and my lowest range, and I count that as a point. Then I go to my highest domain and highest range, and I create that point. So at 3 and -1. So this follows lowest domain, lowest range, highest domain, highest range. What I do is connect it with a line. That creates a linear function that has this domain and range. Now, if I want to create a quadratic, I just make a curve at this point. Okay, so the first one's a linear, and then what I can do is create a quadratic curve. It's just a curve, and that represents a quadratic. We don't have more details, but this is an example of the answer to this question. Okay? One more time, note that this is an example sketch of a linear and quadratic with these characteristics. It is not the only sketch, but it is one of multiple drawings. The idea is that as long as you have the same domain and range as listed in the characteristics, you're good to go. All right, next. So your homework for this is as follows. Page 24, numbers 1 to 7, omit 2. Hopefully you know that omit 2 means do not do. All right, folks, have a numerical day. Take care.